Hi, welcome to chapter 8c, even more time value of money. So in this chapter, we're going to do three things. We're going to look at getting cash at some point in the future and seeing how it grows to an even farther time in the future. So we won't be starting at t equals 0, we'll be starting at some time in the future. And then the second big thing we're going to be doing in this chapter is we're going to be considering if we have compounding periods that aren't annual. So far, we've assumed annual compounding, but in the real world, we often have to think about quarterly compounding, monthly compounding, even sometimes what's called continuous compounding. So we'll take a look at that, and then we'll finish up with an important example of non-annual compounding, which is treasury bonds and corporate bonds. So that's what's coming up right now in Chapter 8c. All right, so far, as I said, we've been looking at projects where we've started at t equals 0, which we always define to be now, and then looking out into the future, or starting into the future and thinking about, well, what about if we come back to t equals 0 now? So now we're going to do something a little bit different. We're going to look at far into the future values of cash flows that we get in the future, not at t equal 0. So let's look at a simple example to see how this works. So we have a single future cash flow. So let's say we're going to get cash flow 1 of $100 in 1 year, and we're going to put that into a project that gets 6% annual compound interest, and we want to know what's the future value at t equal 4 when that project ends. So how could we do this? We could remember that we have the future value is equal to the present value times 1 plus r raised to the t. That's the future value present value formula. And we're going to apply exactly that formula, except let's say something like far future value is equal to future value times 1 plus same old r raised to the TFFV minus, I want that to be a minus, TFV. So it's exactly the same thing we've done before with our present value, future value formula. We're just starting when we get the cash flow, and we're ending whenever we say the project ends or we want to measure our cash. So let's go ahead and see what we've got here. FV at t equal 4 is equal to, we're going to get that 100, okay, and we have 1 plus 6% here, okay, and this is when t equal 4. Let me just put that in parentheses so it's not confusing anybody there. At t equal 4 is equal to 1 plus 6% raised to the, how much time is elapsed that it's growing at 6%. Well, it's going to end at 4, but we don't get it to until t equal 1. So it's got 3 years to grow, right, from t equal 1 year to t equal 4 years. So let's just take this guy and let's put this into Excel, as is becoming usual for us. And let's just see what we've got here. Okay, 119.1. Okay, so if we get $100 a year from now, we put it in this vehicle that provides 6% annual compound interest until 4 years from now. It'll have 3 years to grow, and it will grow at t equal 4. It will be equal to 119.1. So that's what we're doing now. That's the way that this is going to work. So now, as usual, we're going to want a general case for this. So what are we going to want to do? Pretty much when it gets more complicated, right, when we have many far future cash flows, right, more than just one, it's going to be really helpful to draw a cash flow diagram. And then all we're going to do, no fancy formulas involved in this, for each cash flow that we have, we're just going to say the value of the cash flow when we want to measure it in the far, far future, like in the case we just did, it was 4 years away. It's just going to be for each one, what was that cash flow when it first came into our hot little hands or into the project, times 1 plus r to the delta t, and delta t is equal to the t far, far future minus t future, right? In each case, it's the elapsed time. All right, it's the elapsed time that the cash flow is in the project. And once we've done that for every cash flow, we see how much each one grows until the final time we're interested in. Then we just add all of those final values of the cash flows up. So if you're interested, there is a way that you can use summation notation for this. This is a gray page, so of course you're not required to use it. But if you're interested in a general case summation notation formula, those of you that are going to be writing some of these you're going to be working for BlackRock and doing some writing in Python or something like that for their consumer platform, you're going to need to know equations like this. But in this class, you don't need to. All right. So now let's do an example where we have multiple cash flows. And this is actually an interesting real world example from around 2013, which was kind of a transformative time in the uranium industry in this country. So let's see what was going on. Centrus Energy, ticker symbol LEU, which was previously known as USEC, they used electrical energy at the time for their gaseous diffusion uranium enrichment plant. So, okay, that's fine. So they're an uranium enricher operating in this country, publicly traded. And here was their big problem. Gaseous diffusion uses 50 times as much energy as centrifuge plants. And centrifuge plants are the best practice plants in the world right now. So that's a problem. Gaseous diffusion went back all the way to the Manhattan Project when they didn't really care about efficiency, they just cared about getting the job done. But now that we're looking at things commercially for nuclear plants, efficiency is very important. Okay, so USEC was the only enricher of uranium in the United States, and it was at a huge competitive disadvantage compared to everyone else in the world. Okay, so trying to help mitigate that and not go bankrupt. So LEU got together with the Tennessee Valley Authority, which is an electric utility, and they went into a contract that said in 3 years they would pay the Tennessee Valley Authority $89 million for 1,000 megawatts of power to be delivered in the following year, right? And this we talked about a little bit in chapter 1 of the class, chapter 2, that is rather, when we talked about hedging and futures contracts and forward contracts. So the TVA did this so they didn't have to worry about the price of electricity going up a lot in the future. So they'd know they'd be able to plan for their costs. This is a forward contract because it's directly between the TVA and LEU or USEC, right? So a little bit different than a futures contract. That doesn't matter for us here. Okay, so at the time, LEU's bank had an offering for them of a guaranteed 9% interest rate in money market accounts for the next 3 years. So that's the situation. So they have entered into this forward contract with the TVA, and they can put money aside. They want to put some money aside to make sure it grows into enough to pay the TVA in 3 years. And you find yourself working for LEU at this time, and the CEO asks you, will 25 million set aside at the end of each year for 3 years grow to 89 million or more by end of year 3? Of course, putting it in this money market account. And if not, what do you, even though you're just an intern, you haven't even graduated yet, he wants to know your recommendation. Okay, so how are we going to solve this? So first thing that we want to do is draw a free body diagram. All right, so I have a likely looking cash flow diagram right here for us to check out. So as always, we're sitting here at t equals 0 at this very nanosecond, okay? And the CEO has said, what if we put in 25 million at the end of a year into this 9% account, and then another 25 million after 2 years, and another 25 million after 3 years. So this free body diagram you should be able to draw just from like a flash, right? And this is, you'd need to be able to identify who is this free body diagram for, whose perspective is it from? Well, in this case, it's from the perspective of the 9% interest bearing fund, right? The fund is going to get 25, 25, 25, and then the next day after this last tranche of 25, all the money in the fund is going to be pulled out. Okay, so now again, remember, everything in here is growing at that 9% interest. So what we want to do, we need to know the total that's going to be available, represented by this red arrow, to send out from this account to the TVA. So let's take it one step at a time. Okay, so for the 25 that went in at the end of year 3, that's the day before, right? The next day, we send out everything in the account to the TVA. So this has had no time to grow, right? So 25 in, next day, 25 out. Now let's look at this one, number 2 here. What's happening with this one is it's going to have 1 year to grow, okay? So we put it in at end of year 2, it grows by 9%, and look at this, you'll recognize this as the future value formula, the first formula we ever got in time value of money, right? Just this 25 million growing by 9% grows to 27.25 million. And the last one that we have to worry about is the 25 million that we put in a year. And how long does this one have to grow at 9%? It has 2 years to grow, right? 3 minus 1 in most circles is 2. So that's why we've got here, using the future value formula for this tranche, 25 million times 1 plus 9% raised to the 2. 2 years to grow, right? And so that's going to grow to 29.7. And so we just add all these up. That's the total money in the account at the end of year 3 when they're going to send that money to the TVA, and it's 81.95 million. So the key point to remember here is you want to always measure how long the money in whatever vehicle we're talking about has to grow. So not from t equals 0. For this tranche, it doesn't come in until end of year 1. So that gives it just 2 years to grow. That's why we have the 2 in the exponent here. Okay, so now that we've figured all this out, we're ready to tell the CFO that this does not work. It produces less than the 89 million needed. Okay, so far so good. So we've been, good intern and all that jazz. But what if we want to be an awesome intern, right? What would be the next smart thing to do that we weren't asked for specifically? Well, we're sort of asked for it specifically, but let's think about it a little bit. So what could be done to solve this problem? Okay, so clearly a higher interest-bearing account would work. Presumably, the CEO and the CFO are not dummies, and they've already found the highest interest-bearing account they can find that's safe, right? That's going to guarantee that they're not going to lose the money that they put in. So much for that idea. It's a good thought, but practically it wouldn't work. Another idea is to put in more than 25 in each of these tranches, and that definitely is possible. Presumably the CEO has sort of said we're sailing close to the wind, and if we do more than 25, we're increasing our danger of going bankrupt too much. So another possibility here is that we could suggest to the CEO, let's do this 25 million thing, but let's start putting the 25 million in now. So we'll still do 3 tranches of 25 million. We're just going to shift when we put that first tranche in, and therefore skip the last tranche. And now on balance, the funds in the account have more time to enjoy that 9% interest. Now, in this case, of course, we'd have to ask the CEO if the company had a cool 25 million hanging around that they could put into this account today. So let's assume they do. Okay, so let's look at what happens in this case. So in this case, the final tranche to go in is at end of year 2, which conveniently gives it a year to grow at 9%. So that 25 is going to grow to 27.25, just using the future value formula. Okay, and this tranche that comes in at end of year 1 has how many years to grow? 2 years to grow. So we do 25 times 1 plus 9% squared. It grows to 29.7. And now the first tranche that goes in today. So that's going to have 1, 2, 3 years to grow. So we take 25 times 1 plus 9% cubed, and that's going to go to 32.38. And so now we add everything up and we get $89,330,000. Okay, so this would work. So being an awesome intern, we would want to provide the CEO with this other possibility and bring up maybe as questions the idea of putting more in than 25, which could also work if the company had those funds. So just quickly, an important point here on why it is so great and so much better to be a consultant than an employee. So if you're an employee, you do this for the CEO, everything looks good, they're happy, so maybe you get an additional $5,000 in your bonus for the year. But if you were to do this work for the company as a consultant, what you could say is, we found a way to make this work, and not only that, but it gives you an additional $330,000 for you to enjoy at the end of 3 years. And for finding this additional $330,000 for you, we're only going to charge you for this work a fee of $170,000. That's awesome. So always good to be a consultant, in my humble opinion. On. Okay, next big topic in this chapter. Remember, we have 3 big topics. The next big one is compounding periods. And so far, everything I've done, kind of sneakily, has been in annual compounding periods. So what we've meant when we've said R percent interest, is R percent interest per year, and time has always been measured in units of years. And time, of course, can be a real number, doesn't have to be an integer, right? We can look at 2.7 years. There's no finance police that are going to come and arrest us if we do that, okay? But now we're going to get more real worldy, and to do that, we need to be more flexible. So we've got to consider quarterly compounding, monthly compounding, daily compounding, maybe even what's called continuous compounding. And we're going to have to consider other weird things like this, annual compounding paid semi-annually. Okay, so let's see what is up with all this. What are the implications? Well, the good news, and there's pretty much only good news here, is that everything we've done regarding time value so far can be generalized to longer or shorter compounding periods. And to handle non-annual compounding periods, all we have to do is just consistently change our time units. So the future value formula, the fundamental discounting equation, all those things, the closed form equations that we've looked at, they're all going to work. We're just going to have to be very, very careful to change our time units consistently in our interest rates and in T, right? So in R and T. So we going to need to be careful about that. Okay, so a couple important things. So how we talk about this, let's say we're establishing a quarterly compounding period. What we're going to say when we do that, how we're going to describe the interest rate or the discount rate is R percent interest comma compounded quarterly. That way we know there's no question about it. What does that mean? It means R percent interest is paid every quarter, not every year, right? And little r here is always going to be called our native interest rate for, in this case, quarterly compounding, if that's the example we're working with, okay? So little r is always going to be our native interest rate. That's our interest rate with the right time units for this problem, okay? And next thing is that in terms of time, t equals 0 is always going to mean now. And instead of end of year 0, which is what we've been calling it before, it's going to mean end of period 0. Okay. And t equal 1 is going to mean one compounding period from now. So not necessarily a year from now. If, for example, we're working with a problem in quarterly units, t equal 1 is going to mean 1 quarter from now. Okay. So let's see how we talk about some of this for some example native interest rates. So for example, we could say our native interest rate equals 5% compounded annually. That's what we've done before. If we have a problem with monthly compounding, we'd say, for example, R equals 6% compounded monthly. And if we're looking at a quarterly example, we could say, for example, R equals 2% compounded quarterly. Okay, so there might be one other question that you're worrying about here or wondering about here. Where do these R's come from? Well, once again, it's not a law of nature. Okay, so choice of compounding period comes from contractual terms, right? So as usual, there is no law of nature that says treasury bonds have to be done in semi-annual compounding periods. Nothing like that. It's just all the contractual terms of the deal that we're looking at. Okay, so let's do an example now with quarterly compounding to see how this plays out. So let's consider a three-quarter mortgage, and let's go back to Mr. Small Net Worth, right, who's trying to borrow as much as he can, right, to help him purchase the biggest shack that he can find. So Big Shark Lenders comes into Mr. Small Net Worth with a new offer. So they would offer, just like the previous lender, they would offer him $30,000 to buy a $50,000 shack today. So he'd have to put in $20,000 of his own money. They'd give him $30,000. Okay, and their contract would say that Mr. Small Net Worth would agree to pay Big Shark back in 3 equal quarterly payments with 10% interest compounded quarterly. So those would be the contractual terms. So Mr. Small Net Worth might want to know, if I do this contract, how much am I going to have to pay each quarter? So let's see if we can suss this out here. Okay. Now remember, with different compounding periods, different native interest rates, all of our time value equations are still true. We just got to remember to be careful to change our units. Okay. So for example, our fundamental discounting equation, exactly as it's always been, no changes to that. And again, we've just got to remember that in this case, Mr. Small Net Worth is going to have to make payments every quarter, and R is interest compounded quarterly, right? So let's fill that in here. So R is equal to 10% compounded quarterly, right? All right, so that's our native interest rate. R is 10% compounded quarterly, and t equal 1 is now going to mean 1Q from now, 1 quarter from now. Okay. All right, so now let's write out what we've got for Mr. Small Net Worth. So I'm just going to go from this equation and apply it to this problem. Okay, so this is going to be equal to CF times what here? 1 over 1.1 to the what? First one is in 1 quarter, so that's going to be to the 1, right, to keep our units consistent here, plus 1 over 1.1 second payment, 2 quarters out. We're measuring time in quarters, so that's going to be 2, okay, and 1 over 1.1 raised to the 3, okay, and from that we can get, let me just put in here, this is equal to, whoops, 30. Okay, and let's bring this over to Excel and solve it together. Okay, so now through the magic of algebra, I'm going to solve this for CF, right? All right, so let's see if we can solve that. All right, and we get $12,060, essentially exactly what we had found in the previous example. Okay, so that's equal to, all right, so we get 12.6K, which is exactly the same as what we got for the other lender. Okay, so let's just think about this for a second. So, it seems like maybe Mr. Small Net Worth could go with either one, but that's not true. Okay, that would be a big mistake on Mr. Small Net Worth's part to go with Big Shark. Why? Because remember, the other lender figured out that the most Mr. Small Net Worth could pay without going bankrupt was around $12,000 a year. So if he's got to, in this deal, pay $12,000 a quarter, what's going to happen? He's going to not be able to make the payments. He's going to get a visit from some very unsavory characters who are going to grab the title of that shack from him and maybe beat him up along the way, and he's going to lose the shack and lose everything. So that would be a bad deal for Mr. Small Net Worth. But the other key point about this is that, as I said before, all of the equations that we've used before still apply. We just have to be careful to always use consistent units with them.